Okay, so let's repeat the example that I showed you actually in this learning sequence. The example related to using age to predict income of people, right? So I'll call it lecture 032, lecture 32, just lecture 32, and then just let me load the people data. Library read Excel, and then D equal to read Excel people. Okay. So let me just run it. So this is my data set. You have seen this already several times. It's just several variables, like 12 variables plus names, and then that's what we need, right? So the income of people and the age of people. So I would like to make a model which shows income and age, show you all the plots, all the statistics. Well, statistics will be easy because it's calculated automatically, but we will calculate some of the statistics also together to check that the calculated values are correct. So the first is easy. So we just simply take M equal to LM, and then income as a response, age as a predictor, using relationship as a tilde, and then data equal to D to tell that this is not just variables. These are columns of data frame D, right? So let me just LM, not lim, right? And then summary M, which will show you all the statistics. So you can see the statistics. Let me just make it smaller here. So you can see the statistics. This is the intercept. This is the age. You can see the p-value is very small. So if you assume that for population this is 0 and age doesn't influence any income of people, then this is the p-value for this assumption and for this observed effect. So definitely this effect is not observed just by chance, right? Then you can see the R-squared value approximately 0.78. It means 78% of variance of income depends on the variance of age. So 78% of variation of income related directly to the age in our data set. Of course, I'm not talking about all people, right? Now, you can get the predicted values if you simply write YP equal to M dollar fitted values, right? So this is it. And now you can make a plot, like a predicted versus measured plot. You simply write plot, D dollar income, that's our real Y values, and then YP, that's the predicted values. And then you can see indeed we have a predicted versus measured plot here, right? How we can improve it? Well, first of all, you can see the limits are different, right? So it's nice to have the same limits, and also it's nice to show the line for the ideal line, which is has a slope 1 and intercept 0. So let's make these improvements. Well, first of all, I will change the Y limits. I can see that the smallest Y value is 10,000, the largest Y value is probably 45 or 50,000. So let me just use this Y limits equal to C 10,000, 10,000, 50,000, and then I will use the same limits. I will probably make it a separate variable. So limit equal to, and then I will use the same limits here, and also for X. And then I will add also Y lap is equal to income predicted, right? So it will be like DKK per year. Let me use it in squared brackets, the kron per year. And then the same for XLAP, income measure it, or reference, measure it. And then also krona per year, right? I'll also make it blue, color equal to blue. Okay, so let me run it again. And of course I need limits as well. So this is, let me see, xlim, ylim. It should be lim, of course, sorry. It should be just lim because I use this variable lim here, right? Now it should work, and indeed it works. So now you can see we have the same limits for x, we have the same limits for y. And this is the predicted versus measured values. It can be a good idea to add a grid, right? And also to add a line with the ideal slope and intercept, so a equal to 1 and b equal to 0. Let me make it gray, color equal to gray. And then the line type will be, for example, 2, so it's a dashed line. Let me see, AB line. Okay, AB line, like this. And then it should be A 0 and B1. Never remember this. So you can see that this is the ideal line. So if we have an ideal model, if income only depends on age, all points should lie on this line in this predicted versus measured plot. We have actually quite a good model, but not ideal, of course. Okay. Now we can also compute the residuals. So it's simply a difference between the real y values minus the predicted values, right? And now we can make another plot where we have predicted values as x-axis, we have residuals as y-axis, and then I will simply take this xlab here. It should be xlab because now it's x-axis, and then ylab is error of prediction, or I can call it residuals. Yes, it's also Crohn's, right? So these are the residuals plot, right? So you can see this little pattern here. It looks like an error, but most of the points, they look like they randomly scattered on this plot, right? I can also add a line. In this case, I add a horizontal line equal to 0 because, let me just use also color equal to gray, and then LTI equal to 2. So you can see that this is the error equal to 0 level, right? So the residual equal to 0. You can see approximately half of residuals are above this line, and approximately half of residuals are below this line, right? Now I can also calculate, for example, r squared manually. So I can simply say sum of squared y values, right? So sum of squared y values will be sum of the d dollar. Let me make y as a separate variable, so to avoid writing d dollar income every time I need it, like this. Now I can say y mean minus average y squared, right? So that gives me a sum of squared distances between y value and average y. Now I can compute sum of squared errors. It's a sum of errors squared, right? The residual squared. And now r squared is 1 minus sum of squared errors divided to sum of squared distances between y and average y. Let's look at the r squared. You can see 0.7831. And then again, if I show you the summary for m, you can see it's exactly the same value. Exactly the same value, right? You can also compute, for example, standard error, right? In this case, it's sum of squared. It's a square root of sum of squared errors divided to n minus 2 degrees of freedom. In this case, n is 32, and then 2 is 2 the regression coefficients that we estimated, so I need to divide it to 30. So this is standard error. And again, you can see that it's exactly the same as we have. This one is rounded, I believe. Okay. So finally, we can also estimate normality of the residual. So we make a cuckoo plot, cuckoo norm E, and then cuckoo line E. So this is the normality. You can see that it looks pretty good here, right? And then I can also, what I can do, I can also make it Shapiro test, right? So Shapiro test E, and then you can see that indeed the residuals look like they came from normally distributed population. So we can use the normality assumption here, and it confirms that we can trust the model. Okay. Now the regression coefficients, we can show the regression coefficients confidence interval by using conf_int. So this is the confidence interval. You can see that intercept can be negative, can be positive, so it means that it's not significant, right? So we don't know. So most probably the real intercept is 0. Why it is like this? Because our h doesn't have 0 value, right? So our model is made for h between, let me show you the range of the h, okay? So range of $h. You can see in our data set, we have h between 18 and 55. We don't have 0. So model cannot extrapolate, model cannot go beyond these values. So therefore, although in the model we have the intercept, it's not possible to make this model without intercept in this case. You can see intercept is not significant because we have no idea, we have no data points with h equal to 0. The effect from h, you can see it's pretty good. You can see we estimated the effect of h approximately 800, so it means that for a person who is 1 year older, we have 800 euro, or this person earns 800 euro per year more. But in fact, if you think about population, it can be anything between 667 and 993 euro per year, right? So this is the confidence interval. Okay. We can also make a prediction. So in this case, I can say, for example, new y equal to predict m. And now I need to provide my h as a data frame. So I say I should write data frame. Then I need to use the same name as I used in this model. You can see that in the model I used h, so this is also should be h. And then which h I want. For example, h equal to 30, right? So this is the predicted value for h equal to 30. So the model predicts that this h should be 23,753 Danish krona. By the way, I now realize that this was wrong. It was euro per year. Sorry about this mistake. It was not in Danish krona. It's amount of euro per year. So that's the plot. It should be euro per year here. Okay. Now what else I can do? I can actually make a plot where I have the income versus age, the original x and y values, data equal to d. This is my original x and y value. So this is not predicted reference. It's h, x value and y value. And then I can show this new point here. So I can say points, 30 years and y. And then, for example, color equal to red. And then you can see that this is the point, you can see. So actually, I have a person whose age also 30 years old, and you can see that the salary of this person is a bit higher here and is a bit smaller here. I can also show the model. I simply write lm equal lmm, and then I will also make it red line, and then line type equal to 2. So this is the model. Let me just do it again, not lm, of course, AB line. So this is the model, and then you can see the points lies exactly on this model, right? I actually can change 30 to 31, for example, and then make predictions. So let me make a prediction, make a plot again, and then now I can show the points. Now you can see that if I also add the line, the points also line on this straight line here, right? So all the predicted values line on this model line. And now I can also add these uncertainties. You remember how to calculate uncertainty. We need standard error. We have this already, standard error. It's here, right? We also need a t-score. So t-score in this case, I will say qt 0.975. And then you remember it's n minus 2 degrees of freedom, right? So 30 degrees of freedom. So this is my t value, 2.04. And then what I'm going to do, I will say x goes from 20 to, for example, 55, or from 18 to 55. So I generate a lot of x values, you can see, right? Now I can make predictions. I simply say y new equal to predict m data frame h equal to x, right? So I make predictions. So you can see for every h I have a predicted value. And now I can compute this error. So error margin is t times standard error times, you remember, square root 1 plus 1 divided to n plus x minus average. Let me simplify this a little. So first of all, I will compute mx separately. It's mean d$h, that's my x, like this. And then I can compute ssxx is sum d$h minus mx squared. So that will be ssxx, right? And now I can just simply write it here. So it's mx squared divided to ssxx. So that will be the error margin. So for every x value, so for example, the last x value, you can see it's 55 years. This is my estimated predicted y value, 44,510. But this is the error margin. So this is this one plus minus this, right? And then I have this for every value here. And then you can see that for the border values, it's larger. And then in the middle is smaller because the error margin depends on the how far the value is from the average. The x value is from the average, right? Now I can show this just by adding lines. Let's say lines. Let me just do it like this. Lines x, then y new plus error margin, line type equal to 3, let's say, color equal to red, right? So that's the upper boundary, and then the lower boundary is just below, right? So that's it. You can see a little curvature here, right? So not very clear, but still there is a little curvature here. And then you can see, for example, t value is 2, so it means it's 2 standard errors. Remember, standard error is 4, so it's approximately 8.4, right, thousand krona. But in fact, you can see that it's 8.4, somewhere close to 8.4, only in the middle, on the boundaries, on the boundaries of this X range. It's a little bit larger. But this curvature is barely visible because sample size is relatively large, and therefore the distance, the difference between uncertainties is not that obvious. Okay, so that's actually it, and now you know everything, almost everything about simple linear regression. And in the next video, we'll discuss how to extrapolate all this knowledge to multiple linear regression, meaning when you have more than just one X variable.